So thank you very much, Kai, and thank you very much for the invitation. It's really a pleasure to be here and to talk to you. And I mean, since basically 2 years, I'm going now around and talk about this topic, which is now a new research topic also for me, our environmental impact. But I think the most important thing is exactly doing that, going around, discuss together and think together with the community what can actually be done about this. So this is based basically on 2 articles that are both on Nature Astronomy, and you find them also on the archive in case you don't have access. And to give you some context, I would like to start with that. With this curve here, which shows you basically the temperature evolution as measured by oxygen 18 abundance over the last 100,000 years. And what you see is there's a huge variability, but in the last roughly 10,000 years, we have a pretty stable climate here on Earth. And this period is known as the Holocene, and that's basically the period during which all the major civilizations appeared. And now the scientists were asking themselves, okay, we have now the stable period of the Holocene, of the Earth system, but are actually our activities pushing us out of the stable regime? And that's what they call the planetary boundaries. And looking into that, what they found out is that basically the Earth system, there are 9 different domains that are important. You have them here on the circle. And already for 6 of these 9 domains, we are pushing basically the system out of this as a stable Holocene regime. And you see them here. I mean, it's climate change, very well known, but it's also the loss of the biodiversity or land system change. This is basically deforestation. Novel entities, this is pollutions, basically plastic pollution, for example, or the geochemical flows, which is nitrogen and phosphorus that is going in the oceans. So in all these domains, we're doing already too much. And we are pushing the system out of the Holocene, which means we are pushing the system out of the state in which the human civilizations were established. Of course, best known of this is climate change, because you have a thermometer, you can measure the temperature. And what you see here on the left here is basically the same curve as before, the Holocene over the last 2,000 years. We were in fact going towards a little colder climate on Earth, but then all of a sudden something kicked in, and this was the Industrial Revolution. And now we are already at 1.1 degrees Celsius above the temperature at the pre-industrial age. And this is a temperature that was never experienced by Homo sapiens on Earth. So we are already above any of these temperatures that were experienced by humans before. And on the right, you see a zoom in basically. And what is shown here is the black is the observed temperature rise. And then the bands, these are simulations, climate model simulations. And the interesting thing in a simulation is that you can switch off the human. You can simulate, okay, what would have happened if the human wouldn't be there, or if there wouldn't have been an industrial revolution. This is the blue band. And so this is the simulated natural variability of the climate, relatively flat. And then you switch back on the human, and then you get the brown band. And that is why the IPCC says that 100% of the temperature rise currently, the global temperature rise on Earth, is attributed to human activity. And what strikes me personally the most in this graph is that basically I was born around here, end of the 60s. So all this evolution happened in my lifetime. And then you see basically how fast this climate change actually is. And it's really a question of speed, a question of rate with which the climate is changing. And this is really a big concern for the human species. And why this is a big concern, this is another figure from the IPCC reports, where you see projections. You see different pathways, what they call socio-economic pathways. Basically, the red is business as usual. You don't do anything or not very much about it. And then at the end of the century, you have maybe plus 4 degrees Celsius. The orange is basically what would happen if all the climate pledges in the framework of the Paris Agreement would be fulfilled. So even if all the pledges would be fulfilled, and we all know they won't, we still would end up with 2.5 degree. And what basically the climate agreement, the Paris Agreement says is the blue curves, we should stay below 1.5, 2 degrees Celsius. And the reason why we should do this, you see it on the right-hand side, there's the same scale here. And these are different risks. And it's obvious, I mean, white is no risk, yellow is moderate risk, and then red or Bordeaux is high or very high risks. And you see very clearly, I mean, when we go to these curves, orange or red curves, everything turns red. I mean, everything will go just out of control. There's no way how you can control this anymore. There will be risks at all levels. And the final thing I wanted to show you, because I think for me it's always very striking, is because we always speak about we or us, but we are not all in the same boat. We are not all in the same situation or not all the same contribution to this problem on Earth. And what you see here is basically by regions on Earth, so Africa, Asia, India, Latin America, Middle East, China, Russia, Europe, United States. You see the different populations in terms of the size of these circles. And here the populations are divided in deciles. So there are in fact 10 circles, but sometimes they overlap, so you cannot distinguish them. The y-axis is the carbon footprint per person living in this area. And the colors is the income of the person. So if it's blue, it's a very low income. If it's yellow, red, it's higher income. And if it turns gray or black, it's very high income. So you see a very clear correlation. And you see that even in our country, in Europe, for example, I mean, not everybody contributes the same. Depending on what the income is, the carbon footprint is higher. So we also have to bear this in mind that not everybody is contributing the same way to climate change. And I also wanted to show this so you get a feeling of the numbers. We are talking about typical carbon footprints, 10, 20, 30, 40 tons per person per year. Now turning to astronomy. So there are actually in the literature now a couple of estimates of carbon footprint of astronomical communities like the Netherlands or Australia, or individual labs like MPIA in Germany, or IRAP in France, so in Toulouse. This is my lab. So the first thing that you see here on this figure is there are huge differences. And of course, you wonder why are there these differences? Well, one reason is, of course, there's a strong impact of the carbon intensity of electricity production. And this you see clearly with Australia. They produce a lot of electricity by burning coal. And when they do supercomputing, it makes a very big part of the carbon footprint. If you would do the same, for example, in France, where we have a very low carbon intensity, this bar would shrink by a factor of 16, basically. So it depends, of course, where you are. But the other thing is, when you do these assessments, you have to be clear what's in fact included and what is not included. So a very big difference between these different assessments is that not everything was, for example, considered in the Netherlands or in the MPIA assessment. For example, like the use of observatory data from observatories was not assessed at all in these estimates. And also the standards they followed to make the assessments were also not always the same. So it's very important that a standard is followed. and that really all sources of greenhouse gas emissions are considered, because otherwise you may miss the elephant in the room. I also put on this plot a very recent estimate of the French research organization, the CNRS. And this is just an average per employee estimate they made, which also does not include everything. This does not include infrastructures, for example. And also there they came up with a number of 14 tons CO2 equivalent per employee per year. So I want now to dive a bit more in this IRAP bar, because in our lab, in fact, we made this carbon footprint estimate. And I want to explain first to you how we did it. And the first thing, and I think probably the most important thing we did, we were 7 or 8 people from the lab who did a training on carbon accounting. Because, I mean, the math is, of course, simple of carbon accounting, but how to do that properly, what to take into account and how to attribute things to your lab, that's not always straightforward. And it was very important to do this training. So we were trained on the bilan carbone method. That's the official method in France, but you could also use other methods like the GHG protocol or the ISO method. They're basically all equivalent. Second point, maybe sounds trivial, lab director announced the start of activities, is very important. We had our lab director behind us, and you cannot do carbon accounting undercover, because you have to access a lot of administrative data and information that you won't get if you don't have a formal agreement by your management. So this was very important for us, that we had a lab director really also supporting us. Now, what to include in a carbon footprint estimate? So the method that we used basically says, look for all flows of energy, materials, services that come into your lab or eventually go out of it, and for which you are responsible, but also on which you depend. And in fact, the question you ask is very simple. If you would take away one of these flows, will you still be able to do your activity? And if the answer is no, you cannot do your activity anymore, this means this flow needs to be included in your assessment. And then, of course, you collect and analyze data. That's the biggest part of the most time-consuming part of the work. And then you report, of course, the results to the lab. And very important also, and we are still in this activity phase here, define an action plan. Because it's, of course, you cannot, as a management, decide, okay, now we do things differently. You have to bring all the people along and make them support this activity. And that is why this takes also a bit of time. Now, what you actually do when you make the carbon footprint computation is a very simple computation. It's just the sum over the boundaries that you define of activity data multiplied by emission factors. So activity data is just how much you consume, how much weight, how much distance, how much cost, and so on. And emission factors, so activity data you get from your administration. Then you have emission factors that tell you how much ton of CO2 is emitted per kilowatt hours or kilogram or kilometer or million euros spent. These you get from databases in general. There are databases in France, in Germany, in Europe, everywhere. IPCC has some, so typically use that for the emission factors. So when we applied this formula to our lab, that was basically what's coming out. So we looked at all different things like electricity use, heating, water, air conditioning, waste, and so on. The meals that we take, the commuting, home to workplace, but also we have internal commuting because we have 3 sites. Our lab is in fact the biggest lab in France, astronomy lab in France, with 3 different sites. Goods and services, we buy a lot of stuff, be it material stuff or be it just services, subcontracts. Computer equipment, external storage, data flow, and then use of observational data from space, from ground, and then of course hotel accommodation and professional travels. It's very interesting, for example, for us, electricity and heating is not really a big factor. It's in fact even smaller than commuting. The fact that basically half of the people use their own car to drive to work. But you see the biggest parts, you see them here. It's you just buy a lot of stuff, and this has just a big footprint, embodied carbon footprint. Of course, professional travel, everybody knows about that. We fly a lot. But then everybody said, I mean, this was never done before. We looked the first time into what's actually the footprint of using data from space telescopes. We use a lot of data from space telescopes. We have a space science lab or ground-based observatories. And this was really astonishing that this is so important. Now, let's look a bit more into details here. Professional travels, I mean, no surprise. So the blue bar here is basically how the distance traveled. And the orange bar is the associated CO2 emissions. And of course, no surprise that the plane kills everything. I mean, all the flying around. Also interesting, in fact, when you do these assessments, you also include, of course, the visitors, like people like me coming here. So it's good for you. I came by train, so it's not in this left bar, but still, I mean, you see, I mean, this is a very important part, is of course due to the flying. What's also typically coming out, I think every lab finds the same thing. You find a lot of literature now about this. It's that not everybody is equal in a lab. This is the Lorentz curve showing basically how many people are responsible for what fraction of carbon footprint in the traveling. If everybody would be the same, you would be on the gray curve, on the diagonal, but that's not what happens. So for example, in our lab, 20% of emission were produced by only 12 people. We are roughly 300 people in the lab. Or 20% of the travelers are responsible for half of the emissions. And that's very typical. When you look a bit in the literature, in some labs, they find that there's a relation between emissions and seniority. It turned out that it's not true for our lab. In our lab, also the young people travel a lot. So there's no strong correlation there. But we found another interesting correlation is that of these half of the emissions of the 48 people, 90% of these people are men. While the average in our lab is that only 75% of the staff members are male. So there's a clear gender correlation, in fact, behind this traveling. So it's also a very interesting finding, which can you make think about what's behind these numbers and how you eventually could act on them. Now, goods and services. So the way how this is assessed typically, and the way how we assess this, is using a monetary estimate. Basically, you relate the amount of money you spend for given services or given goods to the carbon footprint. So we split down all our purchases in different categories, and we assigned an emission to each of these categories using existing databases. So what you see here on this plot is basically the spending on the x-axis, and then for each of the categories, the average emission factor per kilo euro spent. And so the area, in fact, of these boxes, that's the carbon footprint. And you see that typically the average emission factor is something like 365 kilogram CO2 equivalent per kilo euro spent. Now, use of observatory data. So this was not done before, and so here we had really to invent a new method. So what we did was the following. We first looked, we did our estimate was for 2019. So we first looked in what observatories were used by scientists in this year in our lab, and we just looked through the papers, the refereed papers, and noted the list of all the observatories used was 46 space missions. So could be a probe, could be something, a rover driving on Mars or a space telescope, and 39 ground-based observatories. And then for the computation, we used also monetary estimates. We relate basically the carbon footprint of an observatory to the cost of the observatory. For the ground-based is construction cost and operating cost separate. For a space mission, it's only mission cost globally. But for the space missions, we also used an alternative method related to the weight of the satellite. And I'll show you the results later on that. Now, emission factors is more difficult here because they are not in any database. There is no space observatory emission factor in any database. So this we had to gather from literature. And luckily, there was a bit of literature on carbon footprint estimates for astronomical observatories. And we used that to calibrate these emission factors. And then we gathered activity data from literature and the internet. And then, of course, we only had the full footprint of the observatory, but I mean, we won't attribute all of that to our lab because I mean, we share this with many other astronomers. So what we did, we used an attribution method where we basically estimate the fraction of scientists in our lab compared to the community. And we did this by just looking at all the publications, looking how many authors are on all these publications for a given infrastructure, and then counting how many of the authors are from our lab. And typically you get something between 1%, 1 per mil. It's a typical fraction. So that's what we use to attribute a fraction of the observatory to our lab, and which still, even if these fractions are tiny, it still gives a big sum at the end. Now the emission factors, that's the one we came up with. So for space missions, if you base it on the payload wet mass means it's a satellite filled with propellant. That's the wet, and this makes 50 tons per kilogram of satellite. And if you use a monetary estimate, like the mission cost totally, we came up with 140 tons per million euro. For ground-based observatories, for the construction, we found 240 tons, and for operations, a bit more, 250 tons. It's interesting that ground-based things have higher emission factors than satellites, but you can understand this because a satellite has a very, I mean, even an Ariane 5 with a small satellite has weighs 700 tons. If you build like the ELT now, ground-based observatory, it's I think 40,000 tons of concrete you pour and 10,000 of tons of steel. So it's much more material what you do on ground than related to space. And if you are more material, you have a higher footprint. And you see this below. That's just for comparison from a French database. Typical emission factors for different activity sectors, like just insurance, banking, advisory service, 110 tons. It's very similar, in fact, to space missions. And you can also understand this because what ESA finds, for example, that the biggest part of the carbon footprint of a space mission is just related to office work, just paperwork, doing tests and doing a lot of things. And that's basically, if you just do paperwork, it's 110 tons CO2 per million euro. And then, of course, you see other things, architecture. If it becomes more material, you see the emission factors go up. It's very clear. But this also tells you another thing. It will be very difficult to get these numbers, astronomy numbers, lower because we are already on the low side. And it's because even if you make a ground-based observatories, you spend a lot of time of the work just in your office, paperwork, design activities, and so on. So that's already an interesting lesson. And then, of course, you don't read it. Then we had to collect activity data, and this was a huge job. I mean, it's easy to find the weight of a satellite. It's not so trivial to find the cost of a mission. I mean, very often, I mean, the agencies don't really provide these numbers. So you have to do a lot of research to find out these numbers. We didn't manage always to find numbers, so there are little blanks there. So we just left them out. We just ignored them. Our approach was more that we wanted to have a solid lower limit, but we are aware that we may have missed some things. So we are on the low side to some point. And then all the cost data were, of course, inflation corrected to 2019 economic conditions. And then we got a huge table for every space mission, every ground-based observatories, the full carbon footprint over the entire life cycle. So we have a list for 85 infrastructures. We also said, okay, let's attribute an uncertainty for all these estimates. And typically what is recommended for these monetary estimates is an 80% uncertainty. It's because, of course, I mean, it's a very rough estimate if you use these monetary ratios, but still it's a first guess. And then we got the annual carbon footprints by dividing the life cycle footprint by the mission duration or the observatory lifetime, or at least 10 years. It's just not to have peaks if you just launch the satellite or so on. And when we play all this game and we sum all the things together, we got the following. So first we have a life cycle footprint. I mean, this is not very meaningful because you lump things together which may have only a one year lifetime, a freshly launched satellite, and maybe an observatory that's hanging around since 50 years. So that's not so important. What's more interesting is the annual footprint. So it's for every infrastructure divided the total footprint by the lifetime. And you see, for example, for the space missions, we have two different estimates, completely different, one based on the cost and one based on the mass. But both give approximately the same result. It's within the error bars, it's the same number. So this shows you that the estimate is quite solid, in fact, at the end. Because if you use two different passes, you come to the same result. For our lab, I mean, the ground-based annual footprint is lower, but this is a bias because, as I said before, I mean, our lab is a space science lab, so we use much more space instruments than ground-based observatories. And then when you look at the attribution to IRAP at the end, these are the numbers we came up. So almost 4 kiloton of CO2 equivalent per year for all the space missions. So when you look per scientist, this means 27 tons per CO2 per year per astronomer. And then we also, in this work, we extrapolated to the world inventory by doing some bootstrapping. And we came up with a number even higher, like 36.6 tons CO2 equivalent per year and per astronomer in the world. Now, the interesting question, what people very often ask is, okay, that's astronomy. So what about other fields? And unfortunately, I mean, there's no other field that ever has done this estimate. But still, we can play one game. We can, for example, take the S3 roadmap. So the roadmap of European research infrastructures on ground. So this does not include space. When you look up, for example, the 2021 roadmap, you have a nice table with cost numbers. So let's just use the cost numbers for astronomical observatories. I mean, the emission factors for astronomical observatories and play the same game. And then you can divide this by different science topics. So in the S3 report, there are 5 science topics. Astronomy is included, in fact, in physics. So I split this off. So this is physics without astronomy and astronomy. So in S3, in fact, these are lumped together. So you see that physics is an important contributor to the carbon footprint of research infrastructure. I mean, all, of course, have some footprint. But still, I mean, physics plus astronomy together is more than 50% of the footprint. And that's because, well, physics relies on a lot of infrastructures. Another question then that people always ask after the seminar is, okay, well, let's research. But I mean, there are so many other fields in the world. What about military investments and so on? I mean, they must have a much higher carbon footprint. I found, and just in fact last week, I mean, I found this paper, and really I recommend this reading because it's really changing completely the perspective. So very often when you think about carbon footprint, you put yourself in the consumer point of view and basically say, okay, my consumption, how much carbon footprint is related to that. What these guys did, they took a different standpoint. They looked at the investor point of view. So basically, how much carbon is created by €1 invested. And investment means not only financial investment, means also labor. I mean, you're providing basically your workforce and get money for that. So they specifically want to answer the question: in what field should I work to have a low carbon footprint? And so this is a log scale here. You see, I mean, basically the amplitude. Of course, if you work in the electricity business or gas business or mining or or petroleum business has, of course, obviously, every euro invested has a very high carbon intensity. But if you will work on healthcare, education, public administration, and defense, it's a relatively low carbon intensity. And the research, so luckily there's also research in here, scientific research and development somewhere in the midfield. So yes, we are there and we are not marginal. And if you spend €1 on research, it has some impact. So going back to astronomy. So what's the summary of the situation? It's basically it's a very simplified graph compared to the one I've shown you before, the pie chart. So you have a big chunk is research infrastructures, at least in astronomy, but also in physics, but probably also in other domains. Then, of course, other items related to your work, like traveling, of course, buying goods and services and stuff. And then as an astronomer, you have probably also a lifestyle footprint. So I added 10 more tons here. So you have something like 60 tons per astronomer today, per year. Where we should be in 30 years is there. I don't know exactly where, because I mean, some people say, okay, every human should have 2 tons, not more than 2 tons, CO2 equivalent. Can be one approach. The other is that we have all to shrink by a given factor, and it depends on how much you have today, can be a factor of 5, 10, 20. Interesting standpoint. This is Jason Hickel writing this, looking basically at what is the integrated responsibility, because the CO2 in the atmosphere is not the one only emitted today, it's emitted over the entire history. And he said, if you take this into account, I mean, we in the Northern Hemisphere basically have nothing left anymore to emit. So it will be a very tiny level. So these things are basically roughly to scale. And whatever I mean, you can, of course, endlessly debate what exactly should be the target, but whatever the target would be, I think it will fundamentally change how we will do astronomy in the future. I mean, it seems not possible, at least to me, to just keep doing as we do and reaching still these targets in 30 years. Okay, what can we do? So we looked, for example, in what you can call behavioral changes, like stop flying, you take the train, or commuting, you stop taking the car, you take a bicycle, or instead of eating meat, you move to vegetarian meals and so on, extend the lifetime of the computer equipment and so on. So we looked into detail at our lab. So this is a bit of a complex table. So basically the first column here in percentage gives you within, for example, traveling, if you would move away, there are different options. For example, if you would take only the train in France, that would reduce by 19% the emission. If there would be only 2 flights to non-EU countries, it would reduce by 16% and so on. Then we have a second column. This is what we call the restricted scope. This is basically excluding the observatories, because we have little lever arms directly on the observatory footprint. And still, I mean, if you have very extreme things like only taking the train in France, 2 planes in Europe, and 1 plane for non-European countries, you would get down by 20% the footprint of the entire lab. But you see, globally, I mean, these are at the end not so high numbers. So it's very difficult really to get these drastic factors of 5, 10 reductions within these kind of activities. So let's look at the big things like purchase. What can you do about purchase? Essentially, when you have this kind of graph, you have 3 kind of measures. You either can shrink, so you can reduce what you spend. You can spend differently. It's a modal transfer. So instead of, for example, buying cryogenics or chemistry, you buy electronics. But this already means that activity change. You don't do any specific things anymore. Or a magic thing that somehow you can squeeze the y-axis, reduce the emission factor, and very often things that come into mind are eco-design. So when we discuss this in the lab, I mean, the easy fixes are, of course, you neutralize equipment, you buy less, or you extend the lifetime. These are very obvious things where you can, in fact, indeed reduce things. Buying differently, this is more difficult because it means that you stop some activities. So very attractive, and also our lab director says, okay, let's go into eco-design. So far, I don't have any number to show really on eco-design, but we can already have some guesses. So this is from a French report from the French environmental agency, ADEME, 2018, assessing the life cycle footprint of electronic devices. And I used electronic devices because we do a lot of electronics in our lab. And you see television, computer screens, tablets, and so on. And I think the main feature you gather here is the blue color. And the blue color is primary resources. So behind the carbon footprint of many of these electronic devices are just the primary resources extracted from the earth, the minerals, the metals, and all these things. And they make up a significant fraction of the carbon footprint. And whatever you do, I mean, at the end, you always have the same mine. So it's very difficult to make these shrink. And then, for example, the yellow one, this is the other one showing up. This is distribution. And here you can do a bit. I mean, if you have produced things more locally, you have less footprint associated to distribution, or you don't ship by planes like here for the computers, you can do things. But just to illustrate the real issue, I mean, this is an image of a mine, a nickel mine in Russia. And this is just a citation here telling you that the sulfur dioxide emission from this mine were so important in this year 2005, 2070, that only one volcano on Earth had more important sulfur dioxide emission. And that's just one mine. And of course, you see also this red color, though this was not photoshopped. This was just some spills, petroleum spills, I think, into the river and into the lake. So, I mean, they have a huge environmental impact, these mines. And all our real physical world is based on these kind of things. So eco-design is a little bit tricky. So let's see what we can do. But if you read a bit the literature, I mean, it always comes back to that at the end, if you build something with a given size, you won't be able to shrink the carbon footprint. You just can eventually shrink your system. But then, of course, if you shrink your system, what happens? It's the engineer coming along, oh, there's some space left. Let's put another system in there. That's the rebound effect, very well known also. So, I mean, you have to deliberately shrink the system and say, no, we don't add anything other anymore. So it's a kind of degrowth in some sense. So at the end, I mean, it means that if you want to do something there, you really have to touch the core business. Now let's go to the core business of astronomy. That's our observations. And I showed you some data here from ESO, the European Southern Observatory. And just to make it clear, it's not to point ESO in some way. It's just because that's the only example we have today where we can look into numbers, because they are relatively transparent of what they are doing, and they are doing something. So they made a carbon footprint estimate of their operations in 2018. So operating ESO, just running the observatories, 28 kiloton CO2 equivalent per year. A lot, of course, related to energy. Also purchase, like in our lab, purchase goods and services, business travels, freight, commuting, capital goods, a bit waste. And then based on that, said, okay, they draw an action plan over the next years. For example, they installed, that's now already done, solar panels at the site, at the Paranal site. And this reduced by 7.5% this footprint. And then they want to use more sea freight over air freight, gives a reduction, reduce business traveling, extend the lifetime of IT equipment. So this is not zero, but it's just so small that within one digit, it's not making a big difference. But still, with all these measures, they hope to reduce their footprint by 15% over the next years. 4.5 kilotons. You can see all that on the public website. So this is all just public data. But ESO is doing something else. Someone knows? They build the ELT. And they also estimated the footprint of the ELT. 64 kiloton CO2 equivalent just for the construction, and probably an underestimate, but let's take it as given. So this adds up something. And then, of course, you have to operate the ELT. And there's no estimate for that, but eventually they also will increase the overall ESO footprint. There are some numbers, for example, for the carbon footprint of electricity consumption of the ESO sites. And that's very interesting. In 2016, they had on the Paranal, they had liquid gas generators to power the observatory. And this is the brown thing. And on the other side, La Silla, they had already solar panels. But of course, solar panels, they are not zero. They also have a tiny carbon footprint. And then in the night, the La Silla was powered on the grid, Chilean grid. Then they switched, they connected in 2018 the Paranal to the Chilean grid. So they got rid of the gas generators, had the grid connection, and this already reduced quite importantly the carbon footprint. Then in 2020, well, there was Corona, so reduction of the operations reduced the footprint, but then they went up again. And then in 2022, they inaugurated the solar array at Paranal site. And it's in fact interesting because the solar array is running during the day, the observatory is observed during the night. But an astronomical observatory consumes, at least in Chile, more energy during the day than during the night, a little bit more. And that's because of the air conditioning, because they have to cool down the buildings to get them at the right temperature, basically when they open up the dome, so there are no turbulences. So it still makes sense to have solar panels, but still then in the night you need the grid. And that's the predictions for the future, the ELT jumps in. You have to operate the ELT, or you have to build and operate the ELT. And at the end in 2030, the carbon footprint, after all these efforts, connecting to the grid, building a solar array and so on, after all the efforts, will be higher. So, I mean, whenever you look at these numbers, there's a very simple truth. It's very difficult to decarbonize while ramping up. If you just add more stuff, I mean, you're running against the hill somehow. I mean, so you need both. You have to decarbonize, it works, as I've just shown. If you switch to solar panels, it works and so on. But then you have to stop adding things. So you have also to reduce the deployment pace of new observatories. And just to show you something that's not finished, ongoing, I'm just looking actually in the current dynamics, and that's where we are. That's basically all astronomical observatories operating as function of the year. You see a first spike that's in fact interesting, and here it's because that's a space race. That's basically all the space missions initially launched in the 60s, and these were formerly all planetary missions, going to the moon, going to Mars, going to Venus, and so on. And so that's why I counted in here. And you see that in fact we went down a bit. We count down after the space race, and there was a kind of plateau, but then from the 90s on, we start raising, and today we are at a typical increase rate of 3% per year, adding more observatories around the world. So this is space is basically the bluish things, and ground is the greenish things. So what can we do? So, well, the first thing, if you read the IPCC report, it's very clear. I mean, if we want to keep our planet habitable, we have to switch to a sustainable socio-economic pathway. So we have to change the pathway. And also the IPCC is saying this, it concerns, of course, all human activities, and that includes research or astronomical research. And as I think demonstrated, I mean, this implies that we have to do astronomy differently. Of course, the obvious thing is reduce air traveling, but then going further, I mean, you rethink our activities. For example, I mean, this is something which applies specifically to our lab. I mean, we are building a lot of new stuff every year. And we don't have really the time to think about really new technical developments, doing R&D work. And if you do R&D, I mean, this is has much less environmental impact than building just a new observatory. So this could also be some way of doing that, just going out of this race and really spending more time on thinking on and really developing the things that are really worth doing, and not only making something that eventually creates an incremental improvement. Specifically, I think for astronomy, every astronomer will tell you there is so much archival data that never have been analyzed. And I think we can just make a deeper use of the very abundant archival data. Next point is also, I mean, we have to make decarbonization a funding priority. Today, it's very difficult to go to a funding agency and to get money, not to build new stuff, but to decarbonize the existing stuff. For example, even the ESO solar array was not bought by ESO, was not paid by ESO. It was paid by the electricity company in Chile, who now sells this power to ESO. But they have not invested a single euro into that. And I know that from other projects I'm working on, I mean, they always say, well, you want to do something environmental friendly, very nice, but it cannot cost any money. So it doesn't work. And of course, I mean, if you really spend money to decarbonize, you have money to build less, you have less money to build new facilities. And this automatically will create also a dynamics where you build less new facilities. So if you want to make a change, I mean, it implies a systemic change, and this includes, of course, every levels. I mean, you cannot all blame it just on the researchers or all on the agencies. It's all levels: individuals, labs, funding organizations, governments. And I think the last point also for me, I mean, as a community, we are scientists, and the scientists are alerting today, be it the IPCC or also on the biodiversity loss and on all the other domains. All the scientists shout out today that it's really alarming what's going on. And if we still want to be heard, I mean, we also have to basically take our responsibility and to be exemplary in the future. And just to basically show you again the planetary boundaries, but now shown by Kate Roberts, who wrote this nice book about donut economics, and which basically tells you that we have, in fact, two boundaries. I mean, one is, of course, the planetary boundary, what she calls ecological ceiling, sorry. But on the other hand, and this comes also back to the inequalities on Earth, we have the social foundations, and for many communities on this planet, these are not really met. The people don't have enough to eat, they don't have enough water, don't have justice, and so on. So basically, we have to find a way that humanity altogether fits into this donut-shaped thing, so that we rise up those who fall short, but we calm down those who overshoot. Okay, thank you.